lecture. Okay, so in the previous lecture, we just studied about, what it means when we say that we have a stationary distribution. So the only thing that you have to remember is that the process does not become stationary. It won't be as if, let's say, if you land heads today, you will be landing heads forever. No, that's not the case. What happens is the chance that you will observe heads today is going to be same throughout for the next time periods. And we see that this is a very simple example. In heads and tails example, in one coin toss example, you see that the stationary distribution is there from the start itself. But we also saw that this need not be always the case. And we had a look at our NCD model, and the transition matrix looked something like this. So we decided to solve for this. And again, whenever I say that, I'm writing these equations, right? And what are these equations? These equations are all the balance equations. So what this equation in particular represent? So maybe if I, let's say, just want to draw a graph here, what I can say is that let us say this is my state pi 0. Okay, and all of my states, I can list them here, which is like, okay, so I should also list pi 0, pi 1 minus, pi 1 plus, pi 2, and pi 3, right? So I know that I can reach pi 0 from any of these states. So what's going to happen now is, to reach this particular state, I'll have to take into consideration all of these probabilities. Okay, so it shouldn't be pi up there. It should just be, 0 state. Yeah. So let us say state is 0, 0, 1 minus, 1 plus, 2, and 3. Okay. So I know that I can reach my 0 state from any of these states. And then again, I can go from 0 to any of these states. So it won't necessarily be the case that you will reach 0 from each of the states, right? Because if you have a look here, you cannot reach the state 0 from 2 and 3. So these will be 0 automatically, right? There's no way you can reach state 0 from 2 and from 3 directly. So that is what now we are taking into consideration. So whenever I say directly, it kind of means that in one time step. So in one transition, I cannot go from 2 to 0 or 3 to 0. Okay, so that's fine. But let's say if we can go from 0 to 0. So yes, we can go from 0 to 0, and the probability that you will go from 0 to 0 is 1 by 4. So what you can write here is indeed 1 by 4. And in similar manner, you would just write here 3 by 4. Oops, no, sorry, it will be 1 by 4 everywhere, right? So you can reach 0 from 1 by 4 again, and you can again reach 0 from 1 by 4. So that will be your case. And again, whenever you are moving out of 0, what will you have? You can only go again into 0 state, or you can again go only into 1 minus state. So this will happen, let's say, with a chance of 3 by 4. And this happens with a chance of, let's say, 1 by 4. Okay. So this you have. So again, we know that whatever comes in is whatever goes out, right? And whenever we are analyzing our steady state, what it ideally means is that if you, let's say, start in a particular state, it doesn't matter which state you are starting in. The probability that you will end up in some another state will always, remain constant. So that is what we are kind of trying to say here. And again, now if I were to again just, tell you guys what's happening here is, so if you have a look at this equation that you have here, which represents pi j equal to summation over all the i's which are possible from where you can reach the state j. So here what I'm talking about is all the possible sample paths from which I can reach my state 0, right? Okay, so wait, I think, let me just check once. Just give me a minute. Okay. So I'm actually sorry, but I'll have to say, okay, it was good that I did this diagram. Okay, so these equations that I have written here aren't actually correct. And that is why I was even wondering, why do we get a stationary distribution, which is, symmetric everywhere. Okay, so let me just do this bit of thing, this bit of, once again, I would say. Yeah, so I guess what you guys should consider is, yeah. So again, to figure out the stationary distribution, what we will consider is the all the chances through which you can get into state zero, right? So now if I were to write the probability that I will find myself in state zero in longer term will be equal to what? So again, the probability that I am at state zero multiplied by the chance that I will move to state zero again, right? Plus the probability that I am at state minus one multiplied by the fact that I move from state minus 1 to state 0. And similarly, the fact that you are at state 1 plus, and then you move from state 1 plus to state 0. So this is how you will take into consideration all the probabilities, and this will be your balance equation. So again, remember what I wrote previously were the equations of going out from state 0, because what I took into consideration was this 1 by 4 plus this 3 by 4 and subsequent probabilities, right? But that's not what you should do. What you should do is you go from, you take into consideration all the places from where you can go to 0. Okay, so this will be your case. So this will be your equation. So whatever I explained about the stationarity distribution, that will still remain the same. But again, just the calculations will differ here. So maybe let us just do that calculation once again, I would say. So now you won't get something which is symmetric. So now if I were to write for 1 minus, what will I get? I can reach 1 minus from state 0, right? So probability that I am at state 0 and I'll move to 1 minus is 3 by 4. And again, there's no other way I can move to 1 minus from. So that will be it. And now you will have pi 1 plus. And what will this be? So you can reach pi 1 plus again only from pi 2, right? So there is a 1/4 chance that if you are in pi 2, you will go to pi 1 plus. So that's it. And then if you want to write equation for pi 2 now, and again, let me just write this somewhere here. So 1 by 4 pi 2, I can just write it here, 1 by 4 pi 2, okay? And now we have pi 2. So if you look at all the possible ways where you can reach pi 2 from, is from 1 plus. So given that you are in 1 plus, and you'll go to 2 with the probability 3 by 4, right? And again, if you are at 3, you can go to 2 with the probability 1 by 4. So given that you are at 3 and with the probability 1 by 4, you will transition to the state 2. And now at the end, you will have pi 3, where you start here and what you'll have is 3 by 4. So for 1 minus, you'll have 3 by 4. So given that you are at 1 minus and there's a 3 by 4 chance that if you are at 1 minus, you will move to 3. And this is 3 by 4, 3 by 4 again. So you'll have plus 3 by 4 pi 2 and plus 3 by 4 pi 3. So now these will be the 5 equations that you'll have to solve. I am again sorry. I think there was a bit of a confusion the last time, but yeah. Now these will be the equations that you will be solving. So it's only that, these equations have changed. And again, you will have to use the fact that sum of all of these pi i's is equal to 1. So again, you will see that one of these 5 equations will be redundant and will be of no use, and that you can use to verify. So again, remember we did the otherwise, right? And we still got some numbers which is like half, 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 half. And why was that the case? So what we calculated was not exactly, the probability that you will move to a particular state. It was the probability that you will move out of a particular state. So whenever we are concerning ourselves with stationarity distribution, these balance equations are, pi I times Pij. So you move from I to j, and that is how you get your equilibrium for this one particular state. So Now you will just have to solve these equations, and I'll just solve these equations in the break, I guess, and I'll just give you guys the homework to solve these equations, and thus you will get your stationary distribution basically. So maybe I'll do that later on now, and we'll start with what I was supposed to do today. Does this make sense? So again, remember, whenever I'm talking about stationary distribution, what I look at is the ways I can reach a particular state, and I add all of those possibilities, and I know that that will be the chance that I will find myself in state 0. And because we are looking at the steady state behavior, we write pi 0, pi 0, pi 1, and pi 1. Because again, we want the long-term steady state behavior. So that's going to happen, when we say that the chance that you will find yourself in state 0 is same, irrespective of the time. Because you can clearly see that if, let's say, this is of time n, then this and these probabilities are of time n minus 1, right? Because I'm saying that at n minus 1, I'm at pi 0, and at n step, I'll move to 0 again. At n minus 1, I'm at pi minus 1, and at n, I will move to 0 again with the probability 1 by 4, which is exactly what you get. So let me just, I think I should do this. So you get these, so this 1 by 4 comes from this, and this 1 by 4 comes from this, and this as well. And this 1 by 4 comes from this, which is from this. So I guess now that's pretty clear, and these does not matter. So this was what I did earlier, but this is what you should ideally be doing. So I guess, I mean, this is actually a genuine mistake that could have actually happened with anyone. So I guess it's good that now you guys will be aware of how you should not calculate the stationary distribution. But yeah, does this make things clear now? Mihir, Savri?
Yes, ma'am, understood.
Okay, you should say so. Because otherwise I'll just be wondering. Savri, any doubts?
No, ma'am.
Okay, all right. So this is how you will figure out a stationary distribution. And if you solve these equations, and if you even use this normalization equation, you will get some values. And that will be the same as we discussed earlier, but it's just that the equations now are different. So I guess you do get pi 1 minus directly in terms of pi 0. So what you can do is you can use all of these equations, to figure out everything in terms of pi 0, and then add up all these pi 0 plus pi 1 in terms of pi 0 and so on. You get 1, and then you can figure out the value of pi 0, and then the rest of these as well. Okay, so now these are three essential results about the stationary distribution. And the very first one states that, the very fact that if you have a finite state space, that will guarantee you at least one stationary probability distribution. So again, there can be many as well, but there will be at least one. And now if you also know some additional information apart from that you have finite state space, which is about irreducibility of the process, then you can say that there will be one and only one stationary probability distribution. And now, if you know about its periodicity as well, then again, you're guaranteed that there will be a unique SPD in the long run. and the process will kind of settle down every single time. So there is no way that, it won't settle down. So what happens in periodic is that, the chain will keep on oscillating. So let us say if I look at if you look at this example, you see periodicity, right? But again, the periodicity is only of 1 and 1. So this will entail this particular process aperiodic. So what we're looking at, we want to have a look at a process which is not aperiodic. So we can have a look at this particular process. So this process will never ever settle down, right? Because there's no way, you will always keep oscillating from one state to the other. But for this process, there is a possibility because there is a loop from 1 to 1. So whenever you have this self-referencing loop, you know that the process will settle down. And again, the very fact that you have a self-referencing loop will render this particular process aperiodic. So I guess that is what the result is trying to say. So these three are the main results of stationarity. But again, this is not what we'll be looking at today. So today we'll be looking at something else. And again, let me just share my screen again. Yeah. So today what we'll be looking at is something similar to what we just saw. So again, the questions that we will be trying to answer are still the same, but we are changing the circumstances and we are changing the kind of information that we know. So up until now, what was given to you in the question was transition probabilities. You knew the probability of moving from one particular state to another. But is that always the case? No, right? Because whenever you observe real life world processes, you never know the probability to start with. So you'll have to estimate that probability from something that you know whenever you are starting off with, whenever you have some information, right? So we'll have a look at how to do that in today's lecture. So let me just start off with assuming. So now again, I'm making an assumption that I know my transition rate. So we'll start off with a very basic example. And the example that we'll be learning in this particular chapter, which is of, you allowed to move only from one state to other. So my one state would be the fact that a person is alive, and the other state would be the fact that the person is dead. So you can clearly see that there will be only one transition from alive to dead, which is of concern to us, because we as insurance company will care only about, if a particular person dies or not. And I know that whatever is on the chance here, 1 minus will be the probability that you will still find yourself alive. So that's something. But again, now let me just assume. So again, see, most of the times whenever you go and you, let's say, take out your policy insurance or something, you will always see that what an insurance company will know is, first of all, the period that the policy covers, right? The policy will never cover infinite time of period. It will sometimes have, 80 years. So it might see, things like, this policy will be covering you up until you reach the age of 80, or let's say for the next 80 years. So in that way, you might define the time that you will be observing a particular policy holder, right? And if at all something happens to that policy holder within that time, which was specified earlier, then that will be of concern to the insurance company. So if you see, the kind of information that the insurance company will have is one of the observation period. So whenever I'm saying observation period, it starts when the policyholder takes a particular policy, and it ends when the time period of that particular policy matures. So that will be your observation period. So that is what company knows, right, from the start. And the other thing that the company will know subsequently, as in when the time passes, is the information whether a particular policyholder was alive or dead by the time. If, let's say, we're looking at life insurance perspective. So we'll see how we will arrive at figuring out the transition rate, which is what I'm assuming that I know for now. using the observation period and the death information that you will have. So for now, just for the first part of the lecture, I want you guys to, trust me with the fact that I will tell you guys later on how to figure out the transition rates. Okay, so now I'm just going to assume that we know the transition rate. And again, whenever I'm saying transition rate, the very first question that comes up is, what's the difference between a transition rate and a transition probability? So just to specify that, whenever I'm talking about a transition probability, it is something for a specified time interval, right? I always say that this is the transition probability for one time step, or so I have a time interval defined in units already. But whenever I'm talking about a transition rate, it doesn't have a specific interval defined. It happens instantaneously. So maybe to say it in other words, what I can say is that transition rate is something which defines how quickly you will move from alive to being dead. And transition probability can be something, so it can be defined as something like the chance that you will be dead if you are alive today in the next time period. So that will be something about transition probability. So again, this chapter and this very concept of transition rate is intrinsically connected with, assuming that the time is continuous. So I'm not assuming that I am moving forward in steps. The death can happen anytime, right? That won't tell you, okay, so this is my first time period and that is when I will die. No, you can die this sounds a bit, but yeah, the policyholder's death can be observed at any time, right? So you have to define it in terms of transition intensity, transition rate, or the force of transition. So these three words are used to denote the same thing, and that will be using Greek letters to denote the transition rate. So this is mu of x. Now you will ask, what is this subscript x? So just to tell you guys, I'm going to define two, not exactly, I'm not defining something new, but again, what I'm saying is, if I write something like this, pxt, what it means is, so this will be the probability that given that a person was alive at x, so here my x denotes some sort of time, but it is measured using the age. So again, what I'm saying is, given that the policyholder was alive at age x, the policyholder will still be alive. So the policyholder is still alive at age x plus t. So this x here represents the age. So as we had already discussed, there are some particular models where the transition probability of moving from alive to dead is not same. Because as we can see clearly here, if you are, let's say, 20-year-old, and let's say if there is another policyholder who is 80-year-old, the probability that there will be a transition from alive to death for each of these two policyholders will be highly depending on the age that you are starting at, right? So this transition rate again makes intuitive sense where it depends on x, which is the age of the policyholder at present. Whenever you are trying to determine its transition from alive to death. So this TPX is just representative of the probability that given that the policyholder was alive at age X, the policyholder will be, the probability that the policyholder will be alive at age X plus T. So this, whatever comes up here in the left of P, is the increment in the time that you are looking at from this place, which is where you are starting off. And again, if I'm writing P here, which is, again, this is, you shouldn't confuse this with capital P. It is still, maybe I should write it again. So this is a capital P, but this will be a small p. So you have X there and you have a T here. And similarly, what you can also write is QXT. So QXT will be the probability that you will find yourself dead at age X plus T, given that you were alive at age X. So that is how you will be representing TQX. And again, if you have a look, a person can either be alive or dead, right? So you know that TQX plus TPX should always be equal to 1. So there's nothing new in that, I would say. This will always be equal to 1 because this is just, you're just moving out of alive state. So you can either be alive or you can be dead, right? So if you're alive, it's TPX. If you're dead, it's TQX. So these two are mutually exhaustive events and exclusive as well. There's nothing else that can happen beyond these two. So it always has to add up to 1. So I guess this is clear. But again, now whenever I'm saying, about transition rate, you will have to assume that it depends on age. So maybe I should just write it here. This is age dependent. And again, now what you will think is, okay, now if my transition rate is age dependent, then is my model still a Markov model? Because what I used to say is that it doesn't matter, right? What has happened in the past to predict in the future, I only need the information of the current state, right? So again, whenever I say that this transition rate depends on X, which is my current age, I am not violating the Markov property. So there are certain assumptions that we'll be making to simplify this particular already simple model, but there will be some assumptions. So let us have a look at that assumptions. So let me just put a heading, assumptions. Okay. So the first assumption will be that, the probability is that, okay. So if you have a look here, the probability that you'll find yourself in a alive state or the probability that you'll find yourself in dead state. So again, whenever you're looking at these probabilities, they will only depend on age. Because again, you know that the probability that you'll go from alive to dead state is dependent on the age, right? As from the example of a 20-year-old and an 80-year-old. So you can clearly see that what you will have is the age dependency here. And again, it only depends on the current state that is involved. So if you are in dead, you can never go back. But if you're in alive, you can only be alive or dead again. So what matters is not what has happened in the past. So it wouldn't really matter, whether you are at this alive stage, if you were alive, because it's kind of given that the very fact that you are at alive stage is because you were alive in all the past times, right? So this age X, let's say if you're alive at 20, it is assumed that you were alive at 19, you were alive at 18 and so on and so forth, backwards in the time. So it doesn't really matter. So here what we are saying is that we want to make this model a Markov model. So, not every time you will directly move from alive to dead. You can also have a healthy, sick, dead model that we discussed in the stochastic processes chapter. So this is just to simplify. So I'm just going to write a heading that this is a two-state Markov model. Okay, so this is what we'll be studying for today's class. Okay, so again, as I said, there will be some assumptions involved. So the very first is of Markov. So again, because we're looking at Markov models, we know that the Markov assumption is satisfied. And again, we can just mention that, the probabilities will only depend on age and current state. Okay, that's it. And now if I were to move to the second assumption, so again, what you can actually do is here you can have pretty complex models and we'll have a look at some sort of those models and how to analyze those behavior. Let's say if you are guaranteed that the Markov assumption does not hold, which kind of makes sense in practicality terms as well, right? Because sometimes if you have a prolonged history in the past of the patient's sickness, then that will be influential in determining the probability of him being dead, given that he is alive today. So not necessarily this assumption will be true always, but this is just a simple example to show you how to analyze if at all this assumption is true. So that is why you have to make this assumption that the probabilities only depend on the age and the current state. So this is unrealistic and this is not expected to happen every time, and that is why you have these assumptions. Okay, so I guess that was clear. And the next assumption that we'll be making is about the time intervals. So again, whenever I'm looking at the probability that a policyholder will be dead, which is what me as an insurance company will have to concern myself about the most. So let us say I'm looking at, so my second assumption is something. So if I say that today is the time X plus T, and my policyholder is alive at X plus T, and I want to figure out what is the chance that this policyholder will die in very short interval from now onwards. So we are kind of trying to figure out the instantaneous chance that this policyholder will die. Oh, so that is why I represent dt, which kind of represents just, a short time interval, which is a very, very short time interval. So again, to write this precisely, what we'll be looking at is what happens to the limit when your dt goes to 0. So we want this to be instantaneously precise about the probability that this person will die. So, okay, so to figure that out, we'll see what we'll do here. But again, just to write this formula first, here you're trying to figure out the probability that the person will die in the next moment. And that will be equal to, first of all, you know that the probability, if you're calculating the probability that the person will die, you for sure know that he was alive at some point, right? So you will have to multiply the transition rate. So the transition rate is mu with subscript x plus t. So this will denote the transition from alive to dead, right? And again, this is for one particular instance. But again, whenever I say dt is a very short interval of time, it might consist of two instances. And what you will have to do is then you will have to just multiply it by dt here. So it's like, converting. So let's say whenever you are told to figure out the speed of a car, if you say it is, let's say, 60 miles per hour, you can also say that, it is equivalent to 1 miles per minute. So it's that kind of a thing that's going on here. So what you have now done is you have just to figure out the probability that this guy will, let's say, die in 1 hour is equal to the rate that this guy dies within a minute multiplied by the number of minutes that there are in an hour. So this is the kind of scenario that's going on here. And again, you expect there to be some sort of a noise. This is not always equal. So to write equality here is not theoretically correct. So what you will do is you will just write an approximation sign. Because again, you see that we are kind of assuming that each minute the speed of the car is the same. That is why we are just multiplying the number of minutes that you have in an hour with the probability of something, with the rate of something happening within a minute, right? So you see there is no equality sign. But again, what you can do is you can actually rewrite this in terms of equality as well. So what you'll have to do for that, you can write in dt q x plus t here equal to mu of x plus t dt plus o of dt. So again, whenever I'm saying that I have added this new term of dt here, it is nothing but, just a small correction term, I would say, for this to be equal always. But in limit, when you assume that this dt goes to 0, so this will be equivalent to assuming that, this 1 hour boils down to 1 minute, then you know for sure that because this rate is true for a minute, and if my dt becomes 1 minute, then there will be a precise equality term, right? So whenever you assume a limit that your dt goes to 0, your O of dt upon dt will also be 0. So again, whenever I'm saying that my O of dt upon dt is, sorry, upon, it won't be upon dt. Yeah, it will be upon dt. So again, what I can actually do is, what I'm saying here is that if my, so just to go back to our speed example, I think that is really nice. So if you are looking at, per hour, and if you multiply it with, the number of minutes you have in an hour with the information that you only have about for a per minute, this will be something like limit when your dt goes to, let's say, 1 minute. So what you will have to do is dt goes to 1 upon 60 or something, right, to convert 1 hour into the minutes. And at that point in time, you will see that this will just be equal to 1, because this will be like 60 minutes you have in an hour upon dt, and I think it's just going to go to 1. But again, in this particular example, what we are looking at, let us say we're looking at, I mean, again, I say that this mu of xt is the instantaneous rate, but let's just define that to one instance as 1 second for now. So if I say that this is the rate per second, and this dt is something which is even smaller than a second. So what you'll have to do is, whenever you're limiting this dt to 0, you're basically trying to, okay, so I'm saying that this dt is 1 second and this mu t is instantaneous. So this mu t has to be smaller than this dt, right? This was 1 hour and this was 1 minute. So this dt is something like, let's say, 1 second, and this mu t is the instantaneous rate of time. So when you are trying to minimize the value of dt, which is, let's say, from 1 second to it being instantaneous, you want this thing to go to 0, because you know that only if this is 0 in limits, this is equivalent to this precisely. So again, that is how you will get this answer here. So, I mean, I know that if I apply limits everywhere, this will become 0. So if I have limits here, I'll have limits here. And this mu of x plus t doesn't in any ways depend on dt. So this will come outside, and what will be left with is let's say, mu of x plus t here, that will be equal to the limit dt goes to 0 and dt q of x plus t upon dt. So this is kind of derived from there using the probability, using this equality. And again, in your books, you will see that they have written t here, and t here. So it doesn't really matter, and they have written a generalized gt here. But again, in terms of words, what this means is, so again, if you guys remember, what happens if we have 0 upon 0? It becomes indeterminate, right? So here, the very fact that when I say that my limit dt goes to 0, and this fraction is 0, says that my numerator becomes 0 much more faster than my dt becoming 0. And that is why you get the answer as 0. Otherwise, you would still have indeterminate. But again, this is something very theoretical. And if you get it, it's really good. And I think you should, regardless of, it being theoretical, you should just try to understand what it is trying to say to you in words. So does this make sense to you guys? So this is my first assumption, and this is, I should just capitalize this, I guess. So this is my second assumption. Any doubts so far? Okay, I'm taking that as a no, but feel free to ask me doubts if you have any. Okay, so now we'll move on to the third assumption that we have. So again, whenever I'm talking about this third assumption, it is just a matter of making our making our calculations simpler. So what I say is that my mu of x plus t is constant. So again, I'm not saying that this is constant forever, because I do know that, my mu of x plus t changing is really required for this thing. But again, what I'm saying is that this is constant for whenever my t takes a value between 0 and 1. So I'm saying that if I change the age of a particular policyholder by just one time period. I mean, so let us say if you're looking at, a policyholder which is aged 20. So mu of 20 and mu of 21 will almost be similar. So what I'm saying is that this mu of 20 will be equal to mu of 20.999, because again, here you don't have that equality, right? So generally what will happen is you look at policyholders in terms of, so you figure out their ages, also considering not only the years, but also months. So let us say if a person you're observing is currently has, past 3 months from a particular birthday, let's say 20th birthday. So you will see that he is 20.25 years old. So because a year corresponds to 12 months, and you have observed, and when you're starting to observe, he is precisely 20 years, 3 months old. So you divide 3 by 12, and what you get is 0.25, and you add up that to 20. So you get 20.25, and that will be the age of your policyholder when you start, let's say, observing them. So by the time he becomes 21, you will still be observing them throughout the months. So that is the kind of time period where I'm saying that this mu of x plus t will remain constant. So it is kind of saying that the rate of a particular policyholder dying is constant till his next birthday or something, because that is when your age changes ideally, right? So I guess these are the assumptions that we'll have to concern ourselves with for now, at least for this chapter. So any doubts so far? So also just to ask you guys, do you guys know the way to solve first order differential equations? Have you guys heard of integrating factor method and separating variables method before? Anyone? Okay, so let me just, yeah. So this is just a technique that we'll be using to solve equations. So sometimes what happens is, let us say you're given this particular equation. So you have that, the change in y with respect to a change in x is equal to x plus 1 times y. So now if I tell you to figure out what will be my value of x given a particular value of, what will be my value of y given a particular value of x, and the other is also true, I mean, you can also do that as well. But let's say for now I'm telling you the value of x is 4. So can you tell me using this equation only, what will be the value of y? No, right? Because you certainly do not know dy by dx. So until and unless I give you this, you can't possibly tell me what will be the value for y. So sometimes even without knowing this dy by dx, you can still come up with an equation which is in terms of x for y using only this and no information else whatsoever. So again, the only other information that you might sometimes need is the boundary condition to figure out the constant in the integration. So let me just walk you guys through once. So the method that we'll be using now is called the separation method. And why do we call it separation? As you see here, you have dy by dx, which is equal to some function of x, which is x plus 1, and some function of y, which is y. So here g of x is x plus 1, and h of y is y. So what you will do is, you will put all the y terms on left hand side and you put all the x terms on right hand side. So you move this dx over there and this hy over here to get to this. So let's see how we will solve that equation once we have done that, separation of the variables. And that is why it's called, the separation method, because you're separating on the LHS all the y's and on the RHS all the x's. So now what you have is dy by y. So you have taken this dx over there and you got x plus 1 dx on the RHS. And now as you know that this is dy, so you can also write this as, 1 by y dy as is equal to x plus 1 dx. So now what you will do is you will integrate both the sides. And again, because this is equal, it will still be equal if you integrate both the sides lightly. So now do you guys remember what is the integration of 1 upon y dy? Anyone? Do you guys remember the rules of integration? So again, what is integration? It is just antiderivative, right? So if you, let's say, derivate log of x, what do you get? So if you do d of log of x upon d of x, you get 1 upon x, right? Yes. And now if you just put an integration on both the sides, this d and this integral would cancel each other. And what you will be left with here is log of x equal to integration of 1 upon x. So that is how you know that if you integrate, you'll of course have to shift this dx over there so that this is a valid integration. And then you'll only be left with, integration of d log of x. This d and this integration will cancel each other and you'll be left with log of x on the LHS. So once you have done that, what you know here will happen now is that this will just be equivalent to log of y. Ideally, it should be log of y plus c. But what I'm going to do is, instead of writing this as C1 and then again, when I, let's say, so let me just write it precisely. So again, I think I should just write log. So natural logarithm of y plus C1, let's say, okay. So this will be equal to again integration of x plus 1 dx. So integration of x will be what? X square upon 2, right? And integration of 1 will just be x. And again, I will have some another constant which is C2 here. So what I will do is, I will take this C1 from here and I'll put it on the other side as minus C1. And now this C2 minus C1 is my constant that I will try to denote as C here. So you see that it doesn't really matter what constants you have on either of the sides, because you can ideally, collate them together and you'll end up with one constant. So it's just better to denote it by C on either of these sides. So it wouldn't make any difference to your calculation of the C. I mean, your C's value could be different because if you put it here, it will be the negative of what's it gonna come here. But at the end, your equation will still be the same. So ideally what you should do is, if you want to figure out the equation in terms of y, it's better to leave the constant on the other side, because ultimately you want to figure out what is y equal to in terms of the other variable, which is x here. So once you have gotten up until here, now you know that you have a simple equation, right? Log of y equal to half of x squared plus x plus c. But now to actually pin down the value of c, what you will have to use is a boundary condition that they have given here. So not always there will be a boundary condition given to you, and not always only one boundary condition will be sufficient. But at least in this case, you did not worry about the other cases. So what you will do is y of 0 is equal to 2. So again, they haven't said that what is the 0 representing in here, but your intuitive mind should ideally say you that this is just my y of x equal to 2 when my x takes a value of 0. So what you will do is, you will substitute x as 0 everywhere, and you will know that the value of y is 2. So what you will do now is, you will rewrite this for the boundary condition as log of 2. So you know that when your when your x is 0, your y is 2, right? and this will be 0 plus 0 plus c. So log of 2 is the value of your c guy here, and that is how you can easily, basically derive the value of c here. Okay, so now what we have done is we have pinned down a particular value of c, which is log of 2, but that is only for this particular case when you observe x as 0. So do you think that will be helpful to figure out the actual value of c in terms of x? So what you will have to do is to figure out the actual value of c. It wouldn't be really helpful for you to figure out just the value of c when your x is 0. So you'll have to try to figure out some other way to use this condition to get to the actual value of c that you can use then to figure out the way to rewrite this y only in terms of the known values. So what will you do? You can again, just do something, let's say like, okay, so now I think, so yeah, I guess that was true. So what we got was log of 2's value as c, right? So this is fine. There is no doubt you will have this answer again. But I want to ask you guys a question. What do you think? So, okay, do you think this will be enough to figure out the value of y in terms of x to figure out the equation? What do you guys think? Anyone? So forget about what they have done here. I mean, you can still do this method as well, but I'm deliberately trying to show you guys some another method. I mean, this is what will come to your minds when you see this, and if you don't know that this is a way to solve it. Can you still use this? What do you guys think? How did I get to here? So I just used the fact that, if my x is 0, I know that my y becomes 2. So that will in a way give me the value for this c. And what I said that this has pinned down the value of c for me because my value of c will remain constant. Irrespective of whatever my x is and whatever my y is. But if I know a particular combination of x and y, I can always figure out my value of c. And this log of 2 will always be the value of c. So now if I were to rewrite this equation, what will I get? I'll have here log of y equal to x squared by 2 plus x plus log of 2. So this is the equation that I have now. And you see that this is fairly easy. And now what I just have to do is put e everywhere. So if I put a here and if I put a e here, this will render me just, y on the LHS. And what I'll have here is something like e raised to x squared by 2 plus x plus log of 2. And again, as you know, e raised to log of 2 will just be 2. So you can rewrite, erase this log of 2 here. And you can write it, times 2. So this will be your answer for the equation of y in terms of x. And I guess which is exactly what they have gotten here. So what they have done is, let me just check what they have done. So they are denoting c as some constant of integration. Okay, so they haven't figured out the value of c, I guess. They have just taken e raised to everywhere. And then, okay, so they have defined a as just, e raised to c. So I guess and then they tried to figure out the value of this a, which is again log of, which is just 2, right? And that is why I guess, e raised to 0 is 1, so a is 2. And if your a is 2, which you take as e raised to c, you get to know that c is just log of 2. But again, this is a bit convoluted method for me at least. So what I used was, I directly used this boundary condition to figure out the answer for my c. And once I got that c, I substituted that c in here. And once I substituted it, I just rearranged the equation in terms of y. Any doubts so far?
Ma'am, the method that you used for
Mashita, can you speak a bit louder?
ma'am,
Yeah,
am I now
yeah, you're audible.
for the method that you used? What are we supposed to write as the explanation, like the brief explanation that we need to give? That what did we give? What did we do exactly?
Oh, so we haven't done anything, which is not similar to this, but this is just a bit convoluted. I mean, this is exactly the same method. You won't have to give any brief because this, what I have shown is the method of separation. There is no other way to do it. But the only difference is that I have figured out first the value of C and then I rewrite the equation. Here, what they've done is they rewrote the equation in terms of Y first and then they figured out the equation of C. So here they are just redefining a new random variable, which we don't need to write because we have already figured out the value of C. So what they're doing here is you can still forget about writing A. You can still go on with, this e raised to C and you can substitute this and you will get the value of e raised to C as 2 and you'll get the value of C as log of 2. And again, you won't have to necessarily uh, brief about this method because this is what the method is. Does this answer your doubt or did I even understand your question?
Sorry, I couldn't hear the last statement that you said.
Okay, so last statement that I said, what did I say? Yeah, I just said that, whenever you will be solving or using this particular method to solve any equation, which is like this, you don't have to give any brief of what you're doing because you can just see that, you separate the variables and that is all that is. And then you're just basically using what is given to you to figure out what's gonna happen next. I don't understand what brief are you even talking about? Like what kind of brief do you expect to write?
The, like the one in this they've written that where C denotes the constant, or and we don't need to do that anything, right?
I mean, yeah, so I mean, you can actually just, you don't always have to write this. No, no. I mean, this is a bit of, I mean, this is just because this is a workbook trying to explain you what's going on. The writing C denotes the constant of integration. I think, I mean, you can still write it for the sake of completeness, but even if you don't write it, I don't think there will be any marks because you certainly are not writing, that this integration of 1 upon y is log of y. I mean, that's just like, and no, you don't have to do that. You can just do, so you can just in short, right, calculating the value of C using the initial conditions. I'm calling it a boundary condition here, using the initial condition and you put this and then you can just say that this is y of x at x equals to 0, 2. So you substitute in, I mean, basically whatever comes to your mind, you can just write it. You don't have to, stick to what's given in the book. But just write it in a way that the examiner will understand what you are trying to do. And let's say even if you miss out on a particular step, they can give you credit for whatever you have done correctly.
Okay, ma'am.
Yeah, I hope that answers your doubt. Okay, so again, sometimes, okay, yeah, good. Let me know if you still have any doubt with that. Okay, so this was one method that you can use. But again, let me just show you guys another example. So sometimes let us say if you have an equation like this. So now tell me, can you use the method of separation? So let us say now if I try to separate this. So first of all, let me just take x over there. I'll have dy by dx equal to x minus x plus 1 by x times y. This is a bit weird, right? Because I cannot necessarily separate these x's on one and y's on one, right? So sometimes the separation method is not of use anymore. So there is another method which will come to your rescue, and that is called the, I don't remember the name, but integrating factor. Yeah. So it's called the integrating factor method. So what happens is sometimes when you have dy by dx, of course, but a function of x multiplied with y, this was previously as well. But again, you have an additional function here. So if you have a minus b here, You can't necessarily separate this x's from a's and x's from b's. You will have to work together. So what you define is you define an integrating factor. You define a new integrating factor, and what it's defined as is something like this. So I think these formulas are given in your table booklet. So you don't necessarily have to worry about remembering what is the formula for integrating factor. But you will have to remember this. I mean, you will have to make sure that this equation, so this formula for integrating factor comes from this equation because they're defining the p of x, which is the function attached to y here in this case. So you can't necessarily say p of x as anything, but you'll have to first rewrite the equation that you're given in terms of this. So let us say this was the equation that we had. So what I will do is I will just rewrite it as dy by dx being not equal to, but let's say plus x plus 1 upon x, which is my p of x, which is a function of x times y equal to x. So now you see this x is my q of x, this is my p of x, right? And now you see that this equation is similar to this equation, right? So now if I were to figure out the integrating factor, which I'll show you guys how to use in a second, it will be e raised to integration of x plus 1 upon x dx for this particular example. Okay. So now once you do that, once you've defined integrating factor, how does this integrating factor help you to solve this complicated looking equation? So let me erase this and this. So let us say this is the equation that we're trying to solve now. And what you'll have to do is, here, once you have figured out the integrating factor, so there is a proof behind this, but again, I'm not getting into the proof of it and everything else, but you can certainly find videos elsewhere and I can maybe try to put up a link. So I'll put up a nice link, I guess, from Khan Academy, which will go into very depth of, how to solve a differential equation for people who might be much more interested of why this integrating factor works the way it works. And I think, it will be clear again from this example itself, how easier it will make your life. So what will happen is, now you have this equation, and once you have figured out that this is your integrating factor, what you will do is, you will multiply this. Let me just go back to give you guys a gist of what we're going to do. Okay, so once you have this integrating factor, you will multiply it on both the sides of this equation. So you'll get dy by dx integrating factor plus pxy integrating factor equal to q of x integrating factor, right? So this will just cancel out, so it doesn't make any difference and the equality still holds because we have multiplied integrating factor on both of these sides equally. So once you do that, what happens now is, if you have a look at this left side, what do you guys observe? Okay, so maybe forget about this. Maybe we can go and approach it from the other way. So if you try to differentiate this guy right here with respect to x, so what I'm asking you to do is d of y e raised to integration of p of x dx with respect to x. So again, I will just resort to using the chain rule here. So you can't necessarily say that this is, this doesn't use chain rule because you can clearly see that my y depends on x. So if you have a look at this equation as well, your y depends on x. So in economics, generally this happens, right? Because your quantity depends on the price and your price also depends on the quantity. So that is when you will also have to use chain rule. But again, here, what you will have is, first you, let's say, keep these as the constant. So this will be as it is, dx, and you'll have dy by dx. Okay. Then what you will do is you'll keep y as constant and you'll differentiate this guy. So if you differentiate this guy, I know that differentiation of e raised to 2x with respect to x is e raised to 2x as it is, and then the differentiation of whatever is in the power, which is 2. So here you will again keep this thing as it is, which is p of x dx. And then you will just have to differentiate whatever is there in the numerator here. So now in the numerator, you have integration of p of x dx. So if you differentiate this guy, what you get is just p of x, right? And now if you have a careful look at this equation, it is exactly the same as this guy right here. So again, if you think that if you differentiate this person, you get this. So now if I put integration on both the sides, then if you integrate this whole term, what you will get is the thing that's in here in the bracket, right? So that is what we will do now. So what you will do is you will put integration on both the sides of this equation, and that is why when you integrate, you will end up with this guy here. And on the, so yeah, I mean, this, they have just rewritten that this is y times the if. So you don't have to integrate this complex stuff, because even without integrating, you know from theory that this will always be equal to y times your integrating factor. And then you will also integrate your RHS, and then it's easy, right? Because your IF again is only in terms of x, there's no y. You can just take your IF on the other side and you'll get equation in terms of y, which we'll see now how that happens. So any doubts in this or the way we are going to use this integrating factor method? Any doubts so far? Okay, so let me just erase all of this stuff for now, and we'll see how to use this particular method to solve this equation that we have now. Okay, so what we have done is we have this equation and we have already figured out our integrating factor. But again, this is just a crude form, right? So what we should do is we should ideally solve this integration, and it's easier to do. So you can rewrite this as e raised to integration of 1 plus 1 upon x dx. So e raised to integration of 1 will just be x, and integration of 1 upon x will be what? Log of x. So you get log of x here. And again, we shouldn't forget our c here, which is the constant of integration. But again, you can see here that they have written that you don't have to bother about this c, but let's just bother about c for now, and we'll see why we shouldn't bother about c in what happens to this c later on. Okay, so now this is our integrating factor, and what I can again rewrite this as, because I know e raised to log of x is just x, this will be x, e raised to x plus c. Okay, so now remember that this is our integrating factor. So let me erase everything else. Yeah, and we move forward here. Okay, so remember what is my IF? It is x e raised to x plus c for now. Okay, good. So I know that I have to multiply each of these that I have with my IF. So let us just do that, I guess. So what you get here is dy by dx. I'm just going to write it as IF for now, plus x plus 1 upon x, y, IF equal to x. So here let me expand. So I'll get x square e raised to x plus c. Okay, so this is what I have now here. And I know that if I integrate both of these now, what will I get? Here I know I'm just going to get y times my IF. So I'm going to write my IF now, which is x plus c. So this is equal to the integration of x square e raised to x plus c dx. So does this make sense? So again, remember, whenever you are writing integration, you should also write dx here. But again, you can just, skip that step if it is not that intuitive to you. But I think it should be intuitive. So what you're kind of doing is you take this d of x from here to there. so that you don't have anything here and you have a d of x here. And here if you have integration and so, okay, no, you can't do that, right? Because there is this plus here, so you can't necessarily do that. But again, what we saw was we differentiated y with respect to x, right? So if we differentiate this thing with respect to x, you get this whole stuff, which is why if you integrate this whole stuff with dx, you will get this back. So you integrate with respect to x on both these sides, and then you will arrive at whatever you have just here. Okay, so now you can see you have this on the LHS and this on the RHS. So what you will now have to do is just figure out these integration again. So now if you have a look, you kind of see that, you have e raised to plus c here. So what you can do is integration of x square e raised to x, and I know I can rewrite my e raised to x plus c as e raised to x times e raised to c, right? So I'll just take that out as the out of the integral because it doesn't depend on x. And again, I can rewrite this as yx e raised to x e raised to c. So now you see why you shouldn't bother with the constant, because this will always cancel out at the end. So that is why it is fine if you do not take your constant here whenever you are integrating the p of x to figure out your integrating factor, because at the end it will always cancel out. So I guess I took c just to show you guys that this will eventually cancel each other out. So once you do that, so maybe just let me write, therefore don't bother with C. Okay, that's it. So now once we have this, we are kind of here, right? So this is what you have it. No, so we are yet to integrate this stuff. So you'll have to figure out the integration of x square. Wait, is it not x square? Let me check. Oh, okay. So there will not be any x here. There will only be a 2 here. Yeah, there is no x here. There is a 2 here. So I think there shouldn't be a x here. There will be a 2 here. And again, this is a 2 and this is also 2. So again, it might spark some confusion and you might see that, okay, now this 2 is just a constant. How is it a function of x? So you can still say it is a function of x, because you can still say it is also a function of y because it's just a constant. It doesn't matter how you define it. It takes the same value forever. For every value of x, you will get the value of qx as 2. So now if you have here 2, what you won't have here x square, it will be 2 times x, all right? So again, here it will be 2 times x, and here again it will be 2 times x. So I guess let me just erase all of this mess and we'll just try to integrate the RHS now. Okay, but let's say if this were x squared instead of 2x, whatever I did would stand correct. Okay, so now once we have that, you have this thing at the RHS. So now you'll have to integrate. No, this is on the LHS. You'll have to integrate this. There should be no y. Okay, so you want to integrate this 2x e raised to x dx. Does anyone know how to integrate this? What formula will you use to integrate this? Anyone?
U into V?
Yeah, you will be using u. I think I heard you correct. So it will be u v dx, right? So you will be using integration of parts to figure this thing out. And again, we remember our I late. And we know that there is no logarithm, there is no inverse trigonometry here, but we do have a polynomial and algebraic equation, which is x here. So we are going to take that as our u. So if I were to write my integration of parts formula, let's say, so we use integration of parts, and the formula is something like u v d of x. This will be equal to u integration of v d of x minus integration of u prime integration of v d of x dx. And again, I mean, this is kind of assuming that my u is a function of x and so is my v. So here, if you have this, I am going to assume my u as x. Let's just take it as 2x and my v as e raised to x. So again, the formula that you use is dilate to determine what you will take as u and what you will take as v. So you know that exponential is very easy to integrate, right? And you have integration with respect to v quite often than u. So what you'll do is you'll leave this e raised to x at the end. So again, what you're going to have is I stands for inverse trigonometry, logarithm, algebraic expression, trigo, and exponential. So if let's say you would have had log of x here, if you would have x and log of x instead of e raised to x, your log of x would become u because L comes before a. So a is this algebraic expression, which is just 2x, some polynomial. So I define my u as 2x and my v as e raised to x. So now I just use this formula. So what is my u is just 2x and my integration of v dx, my integration of e raised to x dx is just e raised to x, right? Okay, now I subtract integration of u prime. What is u prime? Is just the differentiation of this guy, which is 2. And integration of v dx is again e raised to x as it is. And I have a dx here. So now if you were to integrate this thing, what will you have? 2 will just come outside and integration of e raised to x dx is again just e raised to x plus c, which will be your constant of integration, which is exactly what you have here. Okay, so now once you have done that, what you will do is you will just equate them to one another. So you'll have this, you'll have this. So it's like when you integrate this, and when you integrate this, you get this on the LHS and this on the RHS. And once you have that, you can again substitute in the values of x and get the value for c, and then just substitute it over here and rearrange equation of y in terms of x, and that will be your final equation for y in terms of x, which is this in this particular case. So this was just a bit of a background on how you go about solving first order differential equations. So again, we call these first order y because we're only looking at dy by dx. Sometimes you also, I mean, we don't have this, maybe fortunately or maybe unfortunately in this subject. So sometimes you also have d square y upon dx square. So you aren't only looking at the speed, you are also looking at the change in speed, which is the acceleration. So in that case, you will have to use second order differential equations. But we don't have that. So there are other techniques to solve those second order differential equations. So I guess that's about it. And maybe what we should do now is go back to what we studied these techniques for, right? So we studied these techniques to be able to figure something out. Oops, I shared the same thing again. Yeah, so just to recall, we were talking about transition rates, which are also called transition intensities of going from alive to dead state. But again, this is not what we want, right? We want to be able to figure out the transition probabilities. So now we will try to see how do we figure out the transition probabilities when we only know some information about the transition rates. And again, these rates won't be given to you guys. You will have to calculate these rates, and we'll have a look at that next soon, very soon. Okay. So now let us just first figure out, if I know the rates, assuming I know the rates and I've calculated the rates, how do I go about figuring out the transition probability? So again, what will be my transition probability of interest here? Let us say I care about, the survival time. So again, this whole subject is about, survival analysis. So whenever I'm talking about survival, I care mostly about my P of, given that I'm alive today, probability that I will also be alive by X plus T. Okay, when my today is just X. Okay, so now if you have something like this, what are we going to do, or rather what can we do? So again, now we want to figure out this, but to start off with, to maybe figure out the value for this, what we will do is we will not start directly with this. Let's just, even I could not possibly come up with the derivation of this, but this is how you derive it. So what we are going to do is we are going to take P of X, and here we will have T plus dt. So this I'm doing deliberately, and you'll see why am I writing T plus dt here instead of just T, or instead of just dt and X plus T on the other side. So what I'm going to do now is I can say that this is, in terms of words, the probability that I will be alive at X plus T plus dt. So maybe if we can form a timeline, I can say that this is my X, and if this is the T time period evolved, this is my next destination, and then there is some very, very small interval dt, and then this is my another destination right over there. So this is age that I care about. Okay, so once I have that, what am I going to do now? So what I will do is I can also say that, using again the Chapman-Kolmogorov equation, which is nothing else but just saying that the probability that you survive from this to this is just the probability that you survive from this to this multiplied by the probability that you survive from this interval to that interval. So what you're going to do is to write the probability that you survive from X to X plus T, I can just denote it as the probability that I'm at X today and I survive up until T. And this will be multiplied by what? By the probability that I am at X plus T and I survive till dt, right? Okay, so that is what's going to happen. And again, just for the sake of completeness, you can also take into consideration what will happen if you are dead at X plus T. But again, you know that if you are dead here, there is no way you will be alive here. So the probability of that happening will be 0, right? So it's kind of saying that, let's say if you are at X plus T, X plus T plus dt, and we know that we are alive here. I know that from alive, you can either go to alive or dead. But again, to be alive here, you have to be alive in this state. So for the sake of completeness, if you want to write about these state path, you can also write the probability that you are alive here and you will be dead here, which is something like Q of X and T. But again, there is no way you can go from there to there, so it will just be multiplied by 0. So this is of no use. So okay, now we'll forget about that. So what interests us is this. So how can I rewrite this as? If I have T here, P here, X here, so what's gonna happen next? Do I know how to write my dtpxt? Yes, right? No, not quite there yet. So what we have here is q of xt, x plus t dt. And I know that for any tpx and tqx, this is equal to 1. So what you're going to do is just 1 minus all of this equation. So the thing with this guy here is actually it doesn't matter if it's plus or minus. We can always define that the error in terms of negative or in terms of positive. So what you do is you just write it as, the addition. But again, now what you'll be multiplying this with is something like 1 minus. So remember previously you had mu of x. That's it. Or was it x plus t? Yeah, it was x plus t. So because we were looking at x plus t to dt, right? What's going to happen instantaneously in the very short interval of time. So what you'll have here is 1 minus mu of x plus t multiplied by dt and just plus some small error correction term. Okay, so here we have used the assumption 2 again, and just even before we started, we used the assumption 1, which was Markov, which is how we were able to write this equation. Okay, so now once we know the value of this is this, now we'll try to figure out, now we'll try to, we are at least one step in to figuring out the value of TPX, but we're still not quite there yet. So what we'll have to do is, again, actually, the whole formula for this will be given directly in your table booklets, and you don't have to sit and derive this formula, but I'm just showing it to you guys for the sake of completeness. So what we'll have here, what we'll do is, we'll just partially differentiate this TBX with respect to T. And again, if you use the very first principle formula of differentiation, which is like the delta method, what you will have is limits of whenever your time really goes to 0. And again, I'm just writing 0 plus. So what I'm going to write here is, so here what I'll have is f of x plus h ideally, right? And here my h is something which is t plus dt. So what I'll have here is, instead of tpx, I will have t plus dt p of x. And I'll be subtracting from it tpx. So for those of you who might not recall the delta formula, it's that, f of x is written as dy by dx. But again, if you use the first principles, it just means that you're figuring out the slope of the equation. So you take one point, which is f of x, and you subtract from it, so when you subtract it from the another point, which is x plus h, and you divide it by the interval that you're looking at. So this will measure your instantaneous rate of change. So that is the same thing that I'm going to do here. So because this will just be d of f of x, right? This is f of x, and this is f of x plus h. So instead of this, I've written t plus dt here. And again, this will be divided by dt, because that is our measure of time, measure of instantaneous time in this particular case. So now you can easily see that because we know this particular value is just this, you will substitute that over there. So what you will get is limit dt goes to 0, t plus dt of x. So you will just substitute tpx minus tpx mu of x plus t dt plus o dt minus tpx and everything upon dt. So you see this and that will just cancel each other out, right? And if you have a look at this particular, this dt and that dt will also cancel. So this term no longer depends on dt. So what you will have outside is minus of tpx mu of x plus t. And inside you will just be left with plus limit dt goes to 0 and o of dt upon dt. So now is the time to precisely use the fact that this is just 0, right? So now what do you know? You know that I'm differentiation of tpx with respect to t is nothing but minus tpx mu x plus t. So now again, you will have to use the methods of integration that we just learned to figure out this equation. Because again, you have, so this is, let's say your y is tpx here. So you have dy by dx equals to minus of y times again something in terms of the x variable here. So again, you see that you can kind of separate these variables. So again, what I can maybe do is, Yeah. Instead of trying to solve everything, let me just walk you guys through the solution. Any doubts so far? Anyone? Okay. So if you now have a look at this particular equation, this is just a rearrangement of what we have derived, right? We had this thing on the RHS. So again, we wanted to separate the variables. So you have these on the one side and this is on the other side. And now you just integrate both the sides. So if you integrate this side, you get log of TPX, and here you will get this thing as it is. And again, now what you'll be doing is, you want, okay, so let me walk through this. You share, I'm sharing this. Yeah, so what is happening here now is, so again, you want the equation of TPX with the variable t in it, right? But again, as we know, whenever I integrate, let us say if I have t here, and if I integrate it over any limits, let's say from 0 to s, at the end you will end up with the s. But that is not what you want, right? You want a formula for tpx in terms of x, in terms of mu, and somewhere in terms of, basically t at the end. So you want the integrals of your limit to, sorry, the limit of your integrals to be in terms of t. So what you're going to do here is, you will just substitute instead of t s here. It's not going to change anything. S is just another placeholder for the time period. It does not change anything else. So what you now do is, you integrate these over from 0 to t. And when you do that, basically we're just using the separation method that we just learned. So when you do that here, you know what you're going to get is, so let's say if you're integrating from 0 to t log of x, so there is a partial differentiation sign here, right? And this is ds and this is ds. So this will kind of get cancelled, and this d and this integral will cancel each other out. So you will have this thing as it is, which is here, and the limits of integration from 0 to t. And once you do that, if they haven't yet substituted it, but they have just made it equivalent to the RHS. So you are yet to integrate this whole variable, but we'll see if it even needs to integrate. Okay, so now once you have that, what you're gonna do is, you will just rewrite this. So this is the ln of SPX, and so again, remember that our variable is S here, right? We are changing it with respect to ds. So this S will take a value 0 first and then t. So you'll have log of tpx minus log of 0px, equivalent to again what was there in the RHS and the integration sign. So now again, we're saying that this guy is alive at age x, and what is the probability that he'll still be alive today? So that will still be 1. That will always be 1, right? Because there is no time that has been passed. So it is always going to be 1. And now if my 0px is 1, my log of 1 is always 0. So this will become 0, and what you will be left with is only that this is equal to this. So now if you have log of tpx, you can just put e everywhere and you will get your value of tpx in terms of mu, and that's it, and in terms of t. So whenever you will be solving this integral, you will get some answer in terms of t, and that is what you would expect. Any doubts in this? So again, this is actually given in your table booklet on page number 32, this precise formula of how you can convert the transition rates, the transition intensities that you are given into transition probabilities. So now this is the probability, right? This is a probability, but this was the transition intensity. And this didn't use any other information than what you already know. So you will, so when you want to figure out TPX, you will know the T as well, and you will have been given the value of mu. So you can easily figure out the TPX value here. Any doubts in that? So if you see, we only used assumption 1, which was for the very first time we used, Chapman-Kolmogorov equation, and we used assumption 2 then later on, where we said that, the limit of ODT upon DT is 0, but we never used the assumption 3. So what the assumption 3 says is that my mu of x plus t is kind of constant every single time I'm looking at t in between 0 and 1. So if my mu is constant here, what do you guys think this equation of TPX will become? So let us say that this mu is a constant. It doesn't depend on x plus s anymore. So how do you guys think I can rewrite this TPX? So now this is something just like this, let's say ds. What do you think will become of this now? Anyone?
E raised to mu t, but there will be a minus sign you have not written.
Oh yeah, sorry. Thank you very much. Okay, so what I'll have is exactly what Mihir said, but again there will be a minus sign. So what I am gonna do here, because this mu does not depend on t, I'm just gonna get my mu s here, which will take values from 0 to t and not forget my minus here. So this will just be e raised to minus of t mu minus 0, right? Which is nothing but e raised to minus mu times t. So this is exactly what you will get if you assume this transition intensities to be constant for at least a while. So I guess that was it. And so I know we started like half an hour late. So do you guys mind if I continue now, or let's just take a break for 5 minutes, I guess? What do you guys think? And then I'll continue for only half an hour, and then we'll take a break again for 1 hour instead of a 1.5 hour break. Is that all right? You can ask me doubts if you have any. I'm gonna